you so much, Fred. It's great to be here. It's very difficult to compete with the last two speakers. I think who can compete with quantum sensing and that story about koalas? But I do my best. My name is Noushin. Again, thanks for the invitation. It's always good to be here. I'm a nanotechnologist, and often when I introduce myself as a nanotechnology, the quick question after that is what the hell is nanotechnology? So I decided to actually start my first slide as what is really nano, like how small. I know everyone knows that it's very small, but really how small is nano? And so let's dig into that. Let's start with a baseball bat, which is usually about 1 meter. So we're going to walk through from the baseball bat down to the nanoscale. So it's going to be quite a long journey, but bear with me. So take the bat, and it's 1 meter divided by 100. So you get to the size of my fingertip, and that's 1 centimeter. So from here, we're gonna go slowly. So take the width of my fingertip and divide it by 10, you get to the size of needle eye. Get that, divided by 10, you get to the diameter of human hair. And that is the smallest division you will be able to see by naked eye. From now on, you should trust me. So take the diameter of human hair, and not the lens, diameter. From the diameter, divide by 100, you get to the size of a blood cell. That's 10 micrometer. Take 1 blood cell, divided by 100, you get to the diameter of a bacteria, not the lens. The lens is 2.5 micron, almost. Take the bacteria, and from this direction, divided by 10 again, you get to the size of viruses. I mean, viruses are quite different. They can be as small as 30 nanometer, but let's say as an average, a virus is 100 nanometer. Now, it's very, very difficult. Close your eyes. Imagine that you're holding on 1 cold virus in your hand, and I'm asking you to divide that virus by 100. And there you go. You get to the size of half of a DNA, and that is 1 nanometer. 1 nanometer is 1 billionth of a meter. And if I want to define it a bit more scientifically, 1 nanometer means only 5 atoms sitting end to end, only 5 atoms. So it's pretty cool, I know, but that's the wrong heading. I should have changed that heading, but it's Friday night, please forgive me. But why we care about such a small scale? Like, so what? Like, yeah, it's pretty small, so what can we do about it? So I'm gonna start the story from here. This is known as the first computer ever made, and it was the size of the room. And now this is kind of the top picture is the smallest practical computer. It really depends on, sometimes people sell it to you as this, that is the world's smallest computer, but yeah, you can't really use that. But the smallest practical computer that you can really buy it for like a decent price, I think sometimes, yeah, something around $700, you can hold it in your hand. So we kind of moved from what you see here, which is very big, and believe me, it wasn't very smart, to something over there which is way more smarter than this one, and is smaller, is lighter, definitely cheaper. And a good example is the phone you have in your hand is way more smarter and smaller than this computer. So yes, there is value in making things smaller. But what I wanted to talk to you, I have one more example. Again, excuse me that the title is wrong. I put together this slide in a rush. But there is another example. This is the 5 megabyte hard drive, which was shipped by IBM in 1956, and it was over a ton. And they had to put it in that aircraft, and then so many very strong men carried, and that is 2024 is holding 2 terabytes on the tip of your finger. So that's, again, emphasizing that smaller is definitely better in this case. And then we have the electronic computer, again, the first computer, which was portable computer. It wasn't just inside the room, you could carry it. And that is, you need a big truck to carry it. And what you see is the same building in 2021, and that man is holding a tiny chip, which is, again, way more smarter than that computer. So is pretty cool. I can go on and on and on. Again, this title is that the heading is wrong, but the story can go on and on. This making things smaller give us an opportunity to do cool things. For example, the story of the pacemaker in 1950s, people with very weak hearts, they have to stay in the hospital because we didn't have a battery, and then they have to carry something like that, a big battery, and then pulse for the heart to beat. And then the first portable pacemaker was that one. The guy seems to be very proud and very happy, and he didn't know that in like 40 years later, actually from here to here, it's only 8 years later, the first implantable pacemaker. And you can actually see that now we are at the size of like a 2 gram. Here, this pacemaker, the first pacemaker implanted in human body lasted only 3 hours. Then they did another surgery. The second one lasted only 1 week. And that patient actually went through 28 surgeries in his life to change pacemaker one after another, which is another story. But right now, pacemakers can last up to 8 years. Then 600,000 pacemakers per year is been used by people from 5 days old to over 100 years old, and that's the future of pacemaker, which is going to be batteryless. So it's going to receive the pulse from your heartbeat, generate the electricity, and feed it to the device. Again, we talk about the power of what can we do when we make things smaller. So it's not just for the sake of the size. One more example is the story of the hearing devices, hearing aid devices and cochlear implant. So it's hard to believe, but we started from ear trumpet, and that's not fun. It's a real device, so people use it to help them to hear better. And now it's very difficult to see that, but that's the hearing aid. Everything else goes inside the ear, and kind of we got stuck since 2011 because it's very difficult and probably useless to make it even smaller than that. But as a nanotechnology is sometimes it bothers me so much if I only introduce nanotechnology as, yes, we are so good at making things smaller, because there's way more into nanotechnology. And today I want to, again, the heading is wrong, but I want to talk to you about what is the beauty of nano. The beauty of nano is that when you make things very small, and then as Dan presented as the first presenter, when you get into the world of quantum, then things, the materials properties, physical, chemical properties, mechanical properties are going to be quite different than what we used to know of them. The best example is gold. Like gold on the ring on your finger is gold and is yellow. I mean, since childhood, we got to know that that's a normal color of gold. Gold is yellowish, but that's what we see. But if you make the gold as a nanoparticle, and if you make those nanoparticles very, very small, and I'm talking about less than 3 nanometer, and you remember in my slides, what is the size, 1 nanometer? So anyway, when you make it very, very small, then suddenly your gold nanoparticles become pink, and they're very pretty. Very pretty. Not that I like pink, but they are really, really pretty. They're 100% pure gold, and they're still pink. If you make them a bit more smaller, like from 3 nanometer to 2 nanometer, they suddenly become a bit purple. If you can, very difficult, but if you can make them even smaller, you might end up with a gold which is blue or even green. And that is quantum effect, that what we talk about. So when you get to the quantum level, which means quantum is the next level after nano, if I describe it that way. But if you get to that level, things are going to be quite different. Something that used to be very conductive can potentially suddenly become non-conductive, actually very insulator. Or something that is very, very soft can potentially become very, very hard. And that, again, now, why this matters to someone like me is because now we can create new things. I can create pink gold. Can you? No. So then we can actually create new things, which is we can pass behind doing fun things. We can make things which are very useful. And I'm going to give you this The title is wrong. I'm going to give you the example, a story of graphene. I don't know if you've heard about graphene or not, but in 2004, there were two researchers in University of Manchester. Andrea was a PhD supervisor, and Costiel was the PhD student. Actually, he's the youngest human being on the planet who ever received a Nobel Prize. But that's end of the. I've told you, the end of the story will end up with a Nobel Prize. But what they've done, they had a rule in the lab, Friday night experiment. Every Friday, they decided to do something just crazy, no matter if it's end up with something cool or not. And what they've done is, graphite is a very useless material. Somehow, it's the tip of the pencil. It's like very soft and dark and black and sometimes dirty. So what they've done, and that's the structure of graphite. If you look at the graphite from the atomic structure, it's the layers and layers of carbon sitting on the top of each other. That's why when you write with your pencil, you can easily write down, because those layers are going to be removed from the tip of the pencil and they stick to your paper. That's why you can write. So then they use one of these sticky tapes and they stick it on the top of the graphite, they peel it off, and they start doing these crazy things that, what if we use another tape on the top of the previous tape and peel it off? Like how thin we can go. And they say, challenge accepted. So they start going one after another, and magically they come up with the idea of sacrificing the tape, so they end up with a floating, only one atomic layer of carbon in their solution. So it's a very difficult job to do, believe me, but they actually ended up with only one atom layer thick. And that was the invention of graphene. They realized that this material is, the original material is pretty useless, but this material is really, really outstanding from the electrical properties. If you leave one electron here, can you see my mouse? Oh, I don't know why you can see my mouse. If you leave one electron here, the electron gets lost everywhere. But if you leave one electron here, the electron has only 2 dimensions to move around. So there is a high electrical property of that material. Also, the bonding between this layer and the other layer is pretty weak. That's why you can write down. But if you can't, but if you can hold from both ends and pull it, those atoms have nothing to lose in their lives. So they really hold on each other very, very tightly. So they have graphene has a very high mechanical property as well. Anyway, they end up with 2010 Nobel Prize of Physics. And since then, graphene changed the entire sector. That's how we can end up with like the flexible LCDs, flexible solar panels, like the supercapacitors, and also being used in medicine. So that was a very nice story, I think, but I think it can go on and on and on. So it's the same material that we're talking about, is graphite, and that is the structure. As I said, if you can end up with only one layer, you produce graphene, and then if you fold it from both ends, you end up with carbon nanotube, and again, that gives you a lot of cool properties. If you fold it in the way that you create this ball, this is also another type of material. And then, lastly, we're talking about pure carbon. All of that I've told you, it's pure carbon, nothing else. If you ask this nicely, if you ask these atoms to sit in this order, you end up with graphite. Very cheap, useless, dull, opaque, soft, common. Then, if you are nanotechnologists and you can rearrange them and ask them again nicely to sit in a different order, you end up with diamond, pure carbon in both cases. It's brilliant, it's transparent, it's hard, and it's rare. So nanotechnology is not just making things smaller for the sake of making things smaller. There is a lot of innovation and stories behind nanotechnologies, which I only have another 9 minutes. So let me talk to you about some examples of nanotechnology, especially the ones that I am using in my laboratory. So one of the examples is that we're really interested in your breath, especially after you have the schooner of beer. We really wanted to know what is really happening in your breath. I know when you're driving, RBT is going to put you in trouble, but we are interested in your breath in order to pick up something in your breath that is very difficult to pick it up in your blood, because blood is complicated, and then blah, blah, which I'm not going to go into the details. I'm very mindful of some people working on blood in the room. But if there is any, let's put it this way, if there is any disease developing in your body, the chemistry of your body changes, and that chemistry can be picked from different ways, and one way is to analyze your breath. What it means that, for example, finally we get to the point that the heading is correct. So, for example, in case of diabetes, the common practice is that we prick the finger, we measure the glucose level in your blood. But instead of doing that, we can potentially analyze your breath and pick up the biomarker in your breath, which is correlating to the level of sugar in your blood. And that biomarker, if I simplify it, is acetone, okay? So, when the level of glucose in your blood increase, the level of acetone in your breath increase as well. You might say, so then why are we not using it? So the challenge is, if from every one molecule of your breath, one of them is acetone, you will be considered as a healthy person. If in every one molecules of your breath, 2 of them are acetone, you be considered diabetes. So the concentration difference between someone who's healthy and doesn't have a diabetes and someone who's a diabetic patient is 1 extra acetone molecule in every 1 million molecule in your breath. It's very hard to visualize it, so let me visualize it. So the entire Harry Potter series, 7 books, they have 1,084,170 words, which makes the word Dumbledore on page 17 of Harry Potter and Philosopher's Stone 1 part per million. So in order to detect diabetes using breath rather than blood, your device, your technology should be able to search all these 7 books in a matter of seconds and find Dumbledore, not every Dumbledore, no, the one which is on page 17 of Harry Potter and Philosopher's Stone. If your sensor can do that, then you can pick up diabetes by analyzing human breath rather than their blood. You might say, forget about it, but we can. Look at our sensor. This is our sensor. It's my student's finger. It's made of billions of nanoparticles. It's tested towards ethanol. This is not acetone. But this is parts per billion. It's not even million. So we can confidently... Sorry?
Use the microphone.
The microphone. I'm always very loud. People always ask me to just... Yeah, okay, so what we have here is that the sensor can pick up, I would say confidently, 10 parts per billion, which means 100 times more accurate than what we need. And again, if you are struggling to understand how small is 10 parts per billion, that's what ChatGPT told me. So this is the city of 1 billion people, and then you're looking for only 5 of them, if you're looking at 5 parts per billion. Or, for example, the time in 6.3 years, you're only interested in 1 second. Now, you might ask this question, how come such a tiny, tiny device made of tiny, tiny particles, they can pick up very small amount of trace element in a gas? It's very simple. It's all about surface area. So we're going to practice to become a nanotechnologist. Imagine that you have a cube. It's simple, has a length, width, and height of 20 centimeters. I'm not going to do magic. I'm not going to change my cube, not volume, not mass. I am just going to divide my tubes to more cubes. So it's 1 cube, same size, same mass, same volume. I'm just dividing it by more cubes. If I divide it by 8 to the power of 2, then I will have 4 times more surface area. So here, this is the surface area I have, but if I turn this one, actually if I make this one out of smaller cubes, I'm actually creating these surfaces in between which they didn't exist before. So now it's 4 times more. If I divide it further, it's 8 times. If I divide it further, so it means that I am going into the nanoscale. I am making my sensor, or whatever you would imagine, from tiny, tiny building blocks. And I couldn't draw this, but if instead of making my sensor out of blocks with 20 centimeter, I make them out of blocks made of 20 nanometer, then I would have 10 million times more surface area, which means 10 million times more atoms are on the surface waiting to react with that 5 molecules in that 1 billion molecules in the surface. So for me, the chance of capturing that 5 molecules within that 5 billion is much higher if I make my materials from smaller building blocks. And you think that I came up with this idea? No, no, no. These guys came up with this idea. So we inspired by nature, not me, the whole community is inspired by nature. We think that our sensors are pretty cool. Dogs can detect part per trillion. There is no sensor in the world. Theoretically we can, practically we cannot. We cannot detect parts per trillion, but they can. They can smell things 40 feet below the ground. We can't. They can smell cancer, and this is not because their nose is designed differently, not because they have 60 times more olfactory receptors in their nose, but also they have a very intelligent brain. This is a part of human brain, and that pretty useless olfactory system that we have over there. So we have less sensors, and we have dumb brain to analyze those sensors. They have way more, 60 times more, and then that's the size of the part of their brain that can analyze all those data collected from those sensors. But I'm gonna finish with something even cooler. I have another 3 minutes. You think dogs are cool? Look at this army. These are bees, and they are detecting something. They're very busy bees. So you can train bees to smell something for you. It's very, very easy. You only need 8 minutes. You hold the bee, you clip it nicely into this one, and then you train them. You give them 4 seconds of acetone as the odor, as the gas, and then 2 seconds of sugar. 4 seconds, 2 seconds, 4 seconds, 2 seconds. When they smell acetone, they stick their tongue looking for sugar. They know the sugar is coming. Then you install the camera above the bee, and the camera is looking for the tongue. You can carry a box of bees, and then you can train them differently. Each of them are sensitive to smell. And then you can see what type of gases are in your environment. You think I'm kidding? No, no, no. This is a business. Look at this business. Yep, sugar. That's a tongue. Yep, now the gas goes in. Sugar. The gas is coming from here, and then 2 seconds of sugar. And now, that's the camera. That's a tongue looking for sugar, which means that they smell that gas that they've been trained to. And people, and the camera is picked up, and people made a business out of it. You think that is a cartridge of a printer? No, they are bees. They've been inside, they've been trained differently, each of them on a different gas. And the guy is carrying that, and then he has a software, and he can see which one is picking what. They really use them in the airport. They really use them to find explosive material in the airport. The problem, which I'm very grateful because otherwise I wouldn't have any job, is they die after 3 weeks. So then you have to try another bee. But if you buy my sensors, no, I'm kidding.
So the story can go on. I have 1 more minute. What I'm using, I'm not training bees. That was just a funny story for Friday night. I am not also training dogs. This is what I am doing. So what we do is that we make sensors. And I remember we make sensors that are very, very, very smart. That's a sensor. So you can put the sensor there. You can see that that tiny thing over there is a sensor. The rest is electronic. I don't do that. I actually ask people in China to do that. But that's actually my sensor here. And that is the battery. That's the electronic part. That is the sensor. That's the electronic part. We can pick things in human tear. We can pick things in human saliva. We can pick things in human sweat. We don't need to prick the fingers. And lastly, you might think that this is science fiction, but remember in 1960s, we were watching, like our parents probably, watching these cartoons, and they thought that this is a science fiction, and it is a reality right now. You might think that this is Star Trek, science fiction. It became a reality in 2013, science fiction 1980s, and then it became a reality in 2010. So whatever I've told you might seem science fiction on Friday night, but it's either a reality already or it will become the reality very soon. And of course, I give a talk, but everything is done by my wonderful students in the lab. Thank you.